Hello, I am Seema and welcome to part 26 of the chapter Haloalkanes and Haloarenes. In the past few videos, we had been discussing the chemical reactions of haloalkanes. Now from this video onwards, we are going to discuss the chemical reactions of haloarenes. In haloalkanes, I told you that there are three main types of reactions. That is nucleophilic substitution, elimination, and reaction with metals. In the case of haloarenes also, we have three categories. We have nucleophilic substitution. In place of elimination reaction, we have electrophilic substitution reaction, and the reaction with metals is the same. Now I'm just comparing the two so that when you try to memorize the kind of reactions, you know what is in what that you have studied. So it helps, it's a memorization tool. Whenever you take a topic, if you compare it with the similar topics that you've studied before, that tool helps you to memorize the things better. So having said that, let us now come to the reactions of haloarenes. The first reaction of haloarenes, just as we had in haloalkanes also, was nucleophilic substitution reaction. So we'll be doing nucleophilic substitution reaction first in this video and the next video. And then we'll come to electrophilic substitution and reaction with metals in later videos. So let us come straight to this. Nucleophilic substitution reaction in haloarenes. Now what nucleophilic substitution is, I don't think it is necessary to repeat the whole thing again. If you go back to the videos of haloalkanes, you would know what nucleophilic substitution is, what a nucleophile is, and how nucleophilic substitution can take place in two ways. That is SN1 mechanism and SN2 mechanism. What are the factors that determine whether the substitution would take place in one step or in two steps? One step is SN2 and two steps is SN1 reaction. So if you do not understand what I am saying, I would encourage you to watch the previous videos, understand what nucleophilic substitution is. Only then we move ahead and understand what I have to tell you now. In the case of haloarenes, nucleophilic substitution does take place, but the reactivity of haloarenes in comparison to haloalkanes is much lesser. This reaction does not take place happily, and it is only under drastic conditions that such a reaction would take place. What are the reasons? Why do haloarenes do not happily react with nucleophiles, or why nucleophilic substitution does not readily take place in the case of haloarenes? You know, in haloarenes, the halogen is attached to a benzene ring, right? To a carbon of the benzene ring. That is why we call them haloarenes. So the various factors that are responsible for the low reactivity of haloarenes towards nucleophilic substitution, the first factor is resonance effect. So aryl halides or haloarenes are extremely less reactive to nucleophilic substitution due to, number one, resonance effect. Now what is resonance? You have studied about resonance in class 11. This is the haloarene. In resonance, when you have conjugated double bonds means you have alternating double bonds. When you have alternating double bonds, the pi electrons, that is the electrons of the second bond, when they are in conjugation in a benzene ring, they have a tendency to get delocalized. They need not remain fixed between two carbon atoms where they are forming a pi bond. If the next bond is a single bond and then the next one is a pi bond, they have a choice to wobble between them. And this wobbling of the electrons, or movement or delocalization we call it, the wobbling or the delocalization of electrons all over the ring, the pi electrons, they become free to move anywhere. So you would get different structures. When we make these structures with a double bond, a single bond, a double bond, a single bond, it does not mean that these two carbons only would have the double bond. It means that there is conjugation, there is delocalization, there is resonance. So this delocalization of electrons is known as resonance, and resonance leads to stability, right? Now take a look at this chlorobenzene. In chlorobenzene, the chlorine is attached to a carbon of the benzene ring. Now chlorine is a halogen. It has 7 electrons in its outermost shell. So it uses 1 electron to form this covalent bond with carbon. But it has 3 lone pairs of electrons. And now if you look at this, there is conjugation in the benzene ring is what we are already aware of. Imagine this to be the second bond, that is the pi bond. This is a single bond, and these lone pair of electrons now start acting as they can also participate in conjugation. They are also delocalized. You know, bonds can be formed using lone pairs of electrons too. Such bonds are known as coordinate bonds. So these bonds, these electrons, that is the lone pair of electrons, they can also participate in conjugation, and they can also become free and they can start moving around the ring. And whenever there is resonance, whenever you have electrons that can participate in this delocalization, such a molecule is very stable. And a molecule that is stable means that it does not react happily. Right? So take a look now. This is chlorine. It has got its lone pair of electrons. There was conjugation in the benzene ring. There were 3 alternating bonds. Imagine that this lone pair of electrons enters here or comes and joins the next bond, shifts itself and forms a double bond here. Right? If a second bond is formed here, one carbon cannot have more than 4 bonds because carbon has a tetravalency. If it forms 4 more bonds, its octet is complete. Carbon does not form 5 bonds. So now what has happened, this carbon, the moment the lone pair of electrons from chlorine comes and forms a bond, this carbon cannot have 5 bonds. It had 2, 3, 4 bonds already. That was the maximum. So when this lone pair of electrons forms a second bond, the pi electrons, that is the electrons of the pi bond, they are shifted towards the next carbon. They shift their position, and that is what delocalization is. They move, they experience repulsion, carbon cannot form 5 bonds, so the pi bond, the electrons of the pi bond, they just shift to the next carbon. As a result of which, this carbon becomes negatively charged because in the pi bond, 1 electron was of this carbon, but 1 electron was of that carbon, which is the alpha carbon. Now that electron has been pushed towards this carbon, therefore this carbon becomes negatively charged. At the same time, chlorine, on losing its lone pair of electrons to form the bond, even a coordinate bond, if it is formed, if the lone pair is acting as a complete bond, still 1 electron you will assume belongs to chlorine and 1 electron belongs to this carbon. So now this chlorine has a positive charge because it should have had 8 electrons and it should have had the octet with 1 single bond, but that 1 electron has gone away to form the coordinate bond and it now belongs to that carbon. Therefore, it becomes positively charged, while the negative charge has shifted to the next carbon. Now, when the negative charge has shifted to this carbon, what happens? Wherever there is conjugation and there is a charge, the other electrons or the other electrons, they start trying to compensate. Whenever there is a delocalization of charges, other charged particles or other atoms try to compensate for the charged particle. So when negative charge comes here, it is pushed here. A negative electron is not very stable. It tries to form a bond. So this electron or this negatively charged, the negative charge shifts here, resulting in the formation of a pi bond. And at the same time, now this carbon would have 5 bonds which it cannot form. So the moment this negative charge forms a double bond here, this double bond shifts to the next position and comes down here, forming the negative charge here. Now the negative charge has shifted here. Again, the compensation, this negative charge is not stable. It tries to form a double bond. When it forms a double bond, it comes here to form a double bond. The electrons of this second bond, they are moved towards the next carbon. And therefore, the negative charge now comes here. In the last step, this negative charge again forms a double bond here. And the second bond of chlorine is pushed back again. And you get back the same structure, the original structure. And in that way, all resonance structures are, the electrons have traveled around the ring and have come back to chlorine. And this is a continuous process. This keeps happening, keeps happening, keeps happening, keeps happening. And that is what resonance is. And that dance of the electrons, you know, between all the carbons and chlorine, it is like children in the playground. They are having fun. The entire playground is to them. They can go to any carbon. So that kind of a situation leads to stability. They are happier there. They do not want to lose that enjoyment that they are having. So now let us understand why it does not. One, it is more stable, and as a result of which, for nucleophilic substitution to happen, the halogen must leave the molecule. Now, since this bond, due to resonance, has a partial double bond character. Why do we say it is partial? Because it is not a proper double bond. We noticed that due to resonance, it was a double bond in 3 structures, but it came back to a single bond. So we say it is partial, it has partial double bond characteristics. But even if it is a partial double bond is always shorter than a single bond. And a double bond is stronger than a single bond. Imagine there's a rope holding two pillars. And if there are 2 ropes holding them, would the 2 ropes holding be stronger, or would just a single bond be stronger? A double bond is always stronger than a single bond, and the length of a double bond is shorter. When there are 2 bonds, the length is less. So that also makes it more difficult to remove the chlorine. So the chlorine is now not only more strongly attached, it is even closer to this carbon. And the closer it is, the more difficult it is to pull it out. So we say that due to the partial double bond character of carbon chlorine, the carbon chlorine has a double bond cleavage, that is breaking of the bond. The bond cleavage, the energy for breaking the bond cleavage energy, or bond cleavage, the process of breaking the bond, is more difficult than haloalkanes. Therefore, this is the first reason, due to resonance effect, we can explain that haloarenes are far less reactive towards nucleophilic substitution. Then comes the second reason. The second reason is hybridization. Hybridization of the carbon, the alpha carbon. Now in haloalkanes, the carbon to which the halogen is attached is sp3 hybridized. But in a benzene ring, this is an sp2 hybridized carbon. You've studied about hybridization. In sp2, whenever carbon forms a double bond, the hybridization is sp2. If it forms a triple bond, the hybridization is sp. And if carbon forms all 4 single bonds, it has sp3 hybridization. In haloalkanes, the alpha carbon is sp3 hybridized. And in sp3 hybridization, there are 3 p's and 1 s. So the percentage of s is only 25%. But in sp2, here, the s, and there are only 2 p's. So the percentage of s is more. It is 33.33%. Right? If you divide the percentage of S and P character, there are 2 P characters but 1 S character out of 100%. This would be 33.33%. And in sp3 hybridization, there were 4 parts. 25% was S character. So in sp2, the S character is more, and S orbitals are smaller in size. The bond is shorter. And s orbitals, since the bond is shorter, the attraction for the electrons is greater. And therefore, the removal of chlorine in the form of chloride, when we say removing chlorine in the form of chloride Cl negative, it has to take those electrons along with it when it is going away as a nucleophile. So we say hybridization of carbon atom. In haloarenes, the carbon, alpha carbon, is sp2 hybridized, and it is sp3 hybridized in haloalkanes. Now look here, this is sp2 hybridized in the case of haloarenes and sp3 hybridized carbon in the case of haloalkane. The length of an sp3 hybrid bond for this halogen, this CX bond in haloalkanes has a size of, the length of this bond is 177 picometers. And the length of the carbon-halogen bond in the case of haloarenes is 169 picometers. It is a shorter bond. The shorter the bond, the greater the S character, more attraction for the electrons. The stronger is the attraction, the more difficult it is to remove the halogen or the nucleophile, because when a nucleophilic substitution is taking place, a nucleophile is attacking, but the halogen also is a nucleophile. It is also going to leave as a negatively charged particle. So we say sp2 hybridized carbon has a greater S character. So it is more electronegative. Electronegative means tendency to pull the electrons towards itself, the shared pair of electrons towards itself. So it says this carbon is more electronegative in comparison to sp3 hybridized carbon. It is more electronegative and the bond is shorter. Thus it makes it more difficult to break such a bond. Now these were two factors. Two more factors that we have to study. One is the instability of the phenyl cation. Again, I would encourage you to memorize or go back a few videos, see the different kinds of nucleophilic substitution reactions. In SN1 reaction, we said that the SN1 reaction takes place in two steps. In the first step, the halogen leaves the haloalkane and results in the formation of a carbocation, because halogen leaves with the bonded electron. So its own electrons plus one electron of carbon it takes and it moves away. Thereby the carbon species, what is left, the alkyl group, that becomes positively charged. So that is known as the carbocation. It results in the formation of a carbocation. In the case of a phenyl cation which will be formed, let us assume that somehow the molecule manages to pull out the chlorine. The chlorine is simply pushed out because there's nothing actually pulling it out. It is just simply pushed out on its own. It leaves along with the electron, which is very difficult because of hybridization, because of resonance effect. Yet, if it is pushed out, even if it happens, the phenyl cation which will be formed will not be stable. Imagine that the children were playing in the playground and the chlorine by its own will is going to go away. It was also participating in the game. If all kids are playing and everyone is having fun, would one just get up and go away for no reason? That doesn't happen, right? Normally, unless he's sick or unless there's something wrong with him. So the chlorine is not going to leave. And in the case of SN1 mechanism, the halogen must first leave the compound to result in the formation of the carbocation. In the case of arenes, it is known as the phenyl. The carbocation is known as the phenyl cation. If, first of all, it will not be formed. And if it is formed, this phenyl cation, once the chlorine moves away with the electrons, this bonded electron, now there is no delocalization of electrons. Even these electrons which were delocalized in the benzene ring, that delocalization would also be destroyed, which is very difficult. So the resonance will be lost and that is not allowed. The molecules do not allow such a thing, that you just destroy the resonance, because the stability due to resonance is very high. So even if nucleophilic substitution does take place, the SN1 mechanism is completely ruled out. SN1 mechanism is totally not possible because the benzene ring is not going to allow the halogen to be taken away without any reason. Then comes the last reason, the fourth factor, which is responsible for making the haloarenes less reactive towards nucleophilic substitution. The nucleophile. Nucleus is positive. Phile means loving. It loves positive charge because it itself is negatively charged, right? And in the phenyl, that is haloarene, the electrons are already in excess. They are having fun in the playground. There are so many. They have a team of electrons moving around. So, in order for a nucleophile to attack, there should be a positive charge, because it itself is negative and it is coming and attacking a positive part. But if the entire phenyl group and the haloarene has already excess of electrons and they are negative. It already has a lot of negative charge. The negatively charged nucleophile will not be attracted to it. It will only be repelled by it. So for a reaction to take place, at least the two should come together. Only then they would react. If you totally are repelled by the subject chemistry, even if I'm standing here and teaching, you are not attracted, you are not coming to my class, you will not study, there will be no reaction. It is only when there is, okay, this might be interesting, I should take a little, maybe I could just test it. Only if we have interaction would you study or would you understand what I'm trying to tell you. It is the same thing. The electrons, the nucleophile is not attracted, it is repelled. And if it is, you are expecting it to react, and as you are expecting that it goes and reacts, it sees the haloarene and it turns around and moves away because it is getting repelled by it. It is not attracted by it, it is repelled by it. So it just turns around and goes away. Oh, I'm not interested. Too much crowd. So, and you know, it is as if there are two teams and all the players are complete. So one other player comes in and he knows he's not going to get a chance to play because the teams are already full. So he moves away out of the playground and tries to look for some other place where the teams are not complete. And there is positive charge where it can go and get attracted. So, because of possible repulsion, it is less likely for the electron-rich nucleophile to approach the electron-rich arenes. So these are the reasons why the nucleophilic substitution does not readily take place in the case of haloarenes, and SN1 is completely ruled out. If it does take place, it has to be SN2, and that also does not take place happily. It only takes place under drastic conditions. So in the next video, we'll take one example of such a reaction and explain how it takes place, and then under what conditions what can we do to facilitate such a reaction. That is done by substitution in the ortho and para positions, which I'll discuss in the next video. So with this, I'll wind up today's video. If you found it helpful, give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.